Final session of the day. We have a contributed speaker followed by our keynote to kick us off. So without further ado, I'll introduce Jinghui Chen from York University, and he's going to tell us about marginal expected shortfall under dependence uncertainty. So please take it away.
Okay, good afternoon, everyone. And first of all, thank you to Sebastian and Savannah for this great organization. And also thank you to all of you for attending my presentation about marginal expected shortfall under dependence uncertainty. As Sebastian introduced, my name is Jinghui Chen, and this paper is co-authored with Ed Furman and Sheldon Lin. My presentation is divided into 5 sections. Okay. Then let's start with the motivation behind this paper. We are all familiar with the event in this picture, right? It's the 2007 to 2009 financial crisis. And many people emphasize the subprime mortgage crisis triggered the beginning of the Great Recession. That is, when housing price decreased and homeowners started to give up their mortgage, the value of the mortgage-backed security held by the investment banks declined in 2007 to 2008. It caused several investment banks, like Lehman Brothers, right, to collapse in September 2008. And essentially, it's a kind of credit risk, okay? And more recently, we experienced the COVID-19 pandemic. And this pandemic triggered another global economic recession, right? And to stop the spread of the virus, global government initiated the population lockdowns. This policy especially affected the manufacturing industry. And we can say that this is a kind of pandemic risk. And then a question arises on our mind: how to quantify and measure the contribution of this specific risk, such as the credit risk and the pandemic risk, to the overall systemic risk of the market, right? One appropriate quantitative measure is the marginal expected shortfall. Let's review its definition. The marginal expected shortfall of a random variable xj for j equal 1 to d is the expectation of xj conditional on s greater than value at risk of s at level p, and where s equals sum of xi. We use TVRP xjs to denote the marginal expected shortfall. And in the context of Solvency II and the Swiss solvency test, the marginal expected shortfall in here is conceptualized as the risk capital allocation, right? Then, interestingly, we want to know how worst or best this risk contribution can be. It is especially important in the extreme market, such as the Great Recession and the pandemic crisis. We formulate our main research problems as what are the minimum and the maximum marginal expected shortfall of a risk xj in here. And the random vector x here is a member of the random vector family ax in here. These minimum and maximum problems are subject to 3 different sets ax. The first, only the marginal distribution information is known. That is xi distributed as fi, okay? And the second, except for the marginals, partial dependence information is also known from this joint distribution function hi. And the third, the partial dependence information is known from this linear condition, okay? The knot set 2 and 3 in here are subsets of 1.
Sorry, quick question. So okay. Y and S are just exogenously specified? In 2 and 3, there's a Y,
yeah.
There's an S.
Yeah, y is.
Oh, sorry, S is the sign, right?
Yes, S is the sign. Y is, let's say, the systemic risk or background risk in here. Okay. And the section 2 deal with the fully dependence uncertainty case. Here are two main theories. The first is for the upper bound theory. Let's xi distributed as fi and s equals sum of xi. Okay, so and then the upper bound of the marginal expected shortfall here, capital P is equal to the expectation of xj conditional on xj greater than value at risk of xj at the level P. And this upper bound is obtained when xi are commotonic. Note that this capital MP is consistent with the no undercut property of the asset allocation rule. That is, no portfolio should be allocated more risk than a standalone risk in the portfolio. But we prove this upper bound mathematically, okay? And then the next is the same for the lower bound. We have small mp greater than or equal to this expectation of xj conditional on xj less than or equal to value at risk of xj, but at the level 1 minus p here. In figure 3, we plot the lower and upper bounds of the marginal expected shortfall of a risk xj when the marginal distribution functions are standard log normal in here. And the upper bound in terms of P is this line, where the lower bound is this line. And specifically, when P equal to Q in here, all possible marginal expected shortfalls due to dependence uncertainty are located in this solid and the vertical line. And also note that this lower bound here is not always sharp. That's why we have greater than or equal in here, okay? So the conditions for its sharpness are proved in this theory. The lower bound MP strictly equal the left tail value at risk 1 minus P xj is obtained if two conditions are satisfied. First, the probability of xj greater than VR1 minus P xj and S greater than VRPS is equal to 0. And second, the probability of xj less than or equal VR1 minus P xj and S less than or equal VRPS is also equal to 0. So let's see an example when the lower bound is strictly equal in the lower bound theory. We have xi distributed as normal distribution with means mu I and standard deviation sigma I, such that sum of sigma I from I equal to 1 to D and I is not equal to J greater than sigma J. This condition makes we follow these two properties, okay? And then the lower bound of the marginal expected shortfall is small mp equal distance, where the phi and both phi here are respectively probability density function and the cumulative distribution function. Then the lower bound mp is obtained when xj equal mu j plus sigma j times both phi minus 1 minus u, and the xi is equal distance, but I is not equal to j. In this case, the S sum of all random variables equal to this term is counter-monotonic to xj, okay? Then the next section, we add partial information on dependence by assuming structures of factor models. Here is the upper bound theory. We assuming xi equal fi y zi. Fi is the function for the factor models, such that we have y, as I mentioned, it's a systemic risk or background risk. Follow the distribution function h, and zi are independent of y. And the conditional random variable xi conditional on y follow the distribution function fiy. And s here is sum of iy zi instead of sum of xi, okay? Then the upper bound is the capital MFP. Use M to refer to the factor model. It's equal to this integration. And the upper bound again is obtained when the conditional random variable xiy are comonotonic. Similarly, we have the lower bound MFP is greater than or equal this integration. Again, to obtain this integration for the lower bound MFP, there are conditions about the conditional distribution functions fiy. I skipped the discussion because of the time limitation. Then let's see an example when the factor models are the additive background risk models, right? Then we have standard normally distributed random variable xi equal bi times y plus square root of 1 minus bi square times zi, okay? Such that the bivariate random vector xiy follows the bivariate standard normal distributions N2 in here. And the covariance matrix sigma is this one. And also the standard normally distributed random variable zi are independent of y. Then for the unconstrained bounds, we have the capital MP equal this term, and the lower bound MP unconstrained is equal to minus this term. Under the setting of factor model and d greater or equal to 1 over p, the constraint bounds are capital MFP equal square root of 1 minus bj square times this term. And the lower bound constraint this time, small MFP is minus square root of 1 minus bj square times this term, okay? Then in figure 4, we plot the constraint, capital MF and small mf, and the unconstrained, capital M and small m, risk bounds of the marginal expected shortfall of a risk xj at the level 0.95 in terms of different bj here. And we can see by adding partial information, both the lower bound here and the upper bound here are improved, okay? And the marginal distribution here is the standard normal. The right panel shows the degree of improvement is equal to 1 minus capital MF minus small mf over capital M minus the small m. In section 4, we add partial information on dependence by a linear condition. I first introduced the weighted insurance pricing model in the literature. Let the capital pi wxjs equal expectation of xj times ws over expectation ws, and the small pi ws is equal to the capital pi WSS, in which WT is a weight function, okay? And when there exist two constants, alpha and beta in R, such that the expectation of Xj conditional on S is equal to alpha plus beta times S, then the capital pi WXJS is equal to expectation of Xj plus beta times the pi WS minus expectation of S. This equation holds for every weight function W. Note that when WS in here equals the indicator function of S greater than value at risk of S at the level P, we have our marginal expected shortfall. And the small pi WS is the systemic expected shortfall. Then the following theory derives the improved risk bounds. We have no negative and no positive random variable xi follows the distribution fi with mean mu I. Then when a constant alpha and beta in R exists, satisfy this linear condition, we have the improved lower bound of the marginal expected shortfall is equal to mu j, and the improved upper bound is equal to Rj times sum of TVRP xi. Okay, and where Rj is equal to mu j over sum of mu I. And furthermore, the lower bound mu j is sharp if and only if there exists a random variables yi, which has the same distribution function as xi, such that this random vector is jointly mixable. And the jointly mixability is introduced by Rudvan in a series of papers. Then the upper bound is obtained when xi are combinatonic. Let's see a simple example when xi is distributed as standard uniform and d equal to 3. In this case, the mean mu I is equal to 1/2. And then for the unconstrained bounds of the marginal expected shortfall, we obtain that the capital MP equal 1/2 times 1 plus P. And for the unconstrained lower bound, we have small mp equal 1/2 times 1 minus P. Okay, then under the setting of expectation of xi conditional on S equal to 1/3S. So this means the F in here is equal to 0 and the beta in here is equal to 1/3. Then with this condition, the constraint bounds are the capital MLP equal 1/2 times 1 plus P, and the lower bound, the constraint lower bound MLP is equal to 1/2. And we can see there is no improvement for the upper bound for these two. The capital MP is equal to the capital MLP. However, an improvement exists for the lower bound. That is the MLP equal 1/2 is greater than this small mp here. Okay. So, okay, let me draw my conclusion here. The main contributions of this paper are: first, we derive the lower and upper bound and also the corresponding copula to obtain them. When only the marginal distribution information is known, so this xi distributed as fi, it's realistic because we can normally know the distribution for a risk, right? And then second, we derived the improved bounds when except for the marginal distribution, the partial dependence information obtained from the structure of the factor models is also known. The last point is we derive the input bounds when the partial dependence information is obtained from this condition here. Okay, and thank you for your attention.
Okay, thank you very much, Jinghui. Questions? We have time for questions from the audience. Comments, questions? Okay.
Thank you for the talk. Maybe if you can